trace of the matrix A. Okay, this is the first. The second one is the multiplication of all eigenvalues, that is lambda 1 into lambda 2 into lambda 3 up to lambda n is equal to determinant of A. So this result are more important to find the eigenvalues and eigenvector for the 2 by 2 matrices. So this result are very important to find eigenvalues and eigenvector. So first one is the summation of eigenvalues is equal to trace of A. The second one is multiplication of eigenvalues is equal to determinant of A. And the third one is if lambda is equal to 0 is an eigenvalue, then the matrix is not inversible, right? If lambda is equal to 0 is an eigenvalue, then the matrix is not inversible matrix. Okay, so these are some result of eigenvalues and eigenvectors. And now let us look at some deep thing for the eigenvectors. To each distinct eigenvalue of matrix A, there will correspond at least one eigenvector which can be found by solving the appropriate set of homogeneous equation. So now we are moving how to find eigenvectors, right? So we can solve the appropriate set of homogeneous equation, that is if lambda I is an eigenvalue, then the corresponding eigenvector xi is the solution of A minus lambda I into xi is equal to 0. That means if we have the eigenvalue for the matrix A, then if we solve the homogeneous system, A minus lambda I into x is equal to 0, and the solution of this homogeneous system, which is the eigenvector xi for the given matrix A. And we all know that how to solve the homogeneous system. We have so many methods to solve the system of linear equations. That is, we have the Cramer's method, we have the Gauss elimination method, we have Gauss-Jordan method. So using any method we can find the solution of this system, and hence we can find the value of eigenvector. So first of all, for the given matrix we can find the eigenvalues, and for each eigenvalue we can find the corresponding eigenvector using the after solution of the homogeneous system A minus lambda I into x is equal to 0. So this is the way in which we can find the eigenvectors for the given matrices. Now here let us if we continue about our last example, in which we have find the eigenvalue for the matrix A is equal to minus 312 minus 1 4, that is equal to minus 1. Now if we want to find the eigenvector for this eigenvalue, then here if we put lambda is equal to minus 1, so that lambda I minus A, that is equal to minus 312 minus 1 4, that is equal to lambda I minus A, that is equal to 1 minus 4 0 0. And by solving A minus lambda I into x is equal to 0, we will get if we multiply here this matrix with the column vector, that is our eigenvector x1 x2, then we will get x1 minus 4x2 is equal to 0. Here this one into x minus this one into x2, so we will get x1 minus 4x2 is equal to 0, and the second row is equal to 0. So here we have only one equation, x1 minus 4x2 is equal to 0. If we take x2 is equal to t, then we will get x1 is equal to 4t. So here x, the eigenvector that is x1 x2, that is equal to 4t and t. If we take t common, then the eigenvector is 4 1 for the given eigenvalue lambda is equal to minus 1. And the same way for the second eigenvalue lambda is equal to -2, we can find the eigenvector x2 is equal to 3 1. Okay, so in this way we can find the values of eigenvector. Let us look at one more example, which is of finding eigenvectors for the matrix A is equal to 2 1 0 0 2 0 and 0 0 2. Here we all know that we have solved this example, which was example number 2, that here lambda is equal to 2 is the eigenvalue for this matrix with the algebraic multiplicity 3. So now if you want to find the eigenvector, then here lambda I minus a into x. Okay, as we know that the solution of this equation lambda I minus a into x is equal to 0 will give us the value of eigenvector. Now if we solve this homogeneous system, then we will get here from the first row we will get minus x2 is equal to 0. From the second one and third one, the second row and third row is equal to 0. So we have not the pivot for the x1 and x3, so we will let x1 is equal to s and x3 is equal to t. Here this is the example of infinite solution, right? So if we take x1 is equal to s and x3 is equal to t, then and here x2 is equal to 0. That is quite clear from the equation. So here the eigenvectors for lambda is equal to -2 are of the form here x is equal to x1 x2 x3, that is equal to s, x2 is equal to 0, x3 is equal to t, and we can write in the form that is s into 1 0 0 plus t into column vector 0 0 1. So here s and t not both 0, right? So this is the these are the eigenvectors for the given eigenvalue lambda is equal to 3, right? So in this way we can find the eigenvector and eigenvalues. So these are some example ready-made for the students. Here I have written the 2 by 2 matrix A is equal to 1 0 0 2, and this is for the homework for the students. Here 2 eigenvalues, first one is 1 and second one is 2, and the eigenvector is 1 0 and 0 1. So in the same way as we have discussed, student can easily find these eigenvalues and these eigenvectors. So students are requested to quickly note down all these questions for the 2 by 2 matrices of finding eigenvalues and eigenvectors. Answer I have given in this PPT. So please quickly note down all these example. This one is for you to solve as a homework. Okay, so these are the some homework example for the students. Now let us move to the most important part of finding eigenvalues and eigenvectors of matrices of order 3. Till now we have only discussed the example in which we have find the eigenvalues and eigenvectors for the 2 by 2 matrices. Now let us look at the examples of finding eigenvalues and eigenvectors for 3 by 3 matrices. Okay, so let us look at the example. Practically we will solve that example. The question is, find the eigenvalues and eigenvectors of the matrix A is equal to -2, -8, -12, 1, 4, 4, 0, 0, 1. Here question is, find the eigenvalues and eigenvectors for the matrix A, right? So here to find the eigenvalue, the characteristic equation which is determinant of a minus lambda I, that is equal to 0, right? So that is equal to, if we do a minus lambda I, that is equal to minus 2 minus lambda, because here I is a 1 0 0 0 1 0 and 0 0 1, so only the diagonal elements will be changed here by the subtracting by lambda. So is minus 2 minus lambda, here we will get 4 minus lambda, here 1 minus lambda, right? All the rest of the elements are same, so this is minus 8 minus 12, here 4 1 0 0. Okay, this is the determinant, right? So determinant of a minus lambda I, that is equal to 0. Now simplifying, we know how to expand the determinant, so here we will expand this determinant, so we will get here there are two methods to expand the determinant. Here by direct using the idea of determinant we can find the expansion of determinant, or if we want to use the theorem, then the theorem says that the expansion of this determinant is lambda cube minus s1 lambda square plus s2 lambda minus determinant of a, that is equal to 0, where s1 that is equal to trace of a, that is equal to, for this example, trace of a, that is the addition of all diagonal elements, that is minus 2 plus 4 plus 1. So here minus 2 plus 4 plus 1, that is equal to 3. Okay, so here trace of a, that is equal to s1, that is equal to 3. s2 is equal to sum of minors of diagonal elements. Okay, so here to find s2, here first of all we need to show all the minors of diagonal. As we all know, minor of minus 2, that is equal to 4 4 0 1, right? Minor of 4, that is minus 2 minus 12 0 and 1, and the minor of 1, that is minus 2 minus 8 1 and 4. That means if you want to find the minor of 1, then if we delete this row and this column, that will be the minor of this element, right? So minor of 1, that is by deleting this one, that is minus 2 minus 8 1 and 4. So here to find s2, that is the sum of all minors, so here s2, that is equal to, first of all, minor of minus 2, that is equal to 4 4 0 1 plus minus 2 minus 12 0 1, this is the minor of 4, plus minus 2 minus 8 1 and 4. Okay, this is the minor of minus 2, second one is minor of 4, and third one is minor of 1. So by finding the minors, here this one is equal to, first one the solution is 4, second one and this one is equal to minus 2 because this one is 0. Here this is equal to minus 8 and plus 8, that is equal to 0. So the sum of minors of diagonal elements, that is equal to 4 minus 2 plus 0, that is equal to 2. This is the value of s2. and now the S3 is the determinant of A. We all know how to find the determinant for the given matrices. So now I am not wasting the time to find the determinant of A. Here determinant of A, that is equal to, here A is -2, -8, -12, 1, 4, 4, 0, 0, 1. If we want to find the determinant of A, if we are using the third row, then that is the easiest one. So here 1 into -2 into 4 plus 8, that is -8 plus 8, that is equal to 0. So here determinant is equal to 1 into -8 plus 8, that is equal to 0. So here determinant of A is equal to 0. So as we have discussed, we want to find the eigenvalues and eigenvectors for this matrices, and to solve the characteristic equation we are using the method of this one, lambda cube minus s1 lambda square plus s2 lambda minus determinant of A is equal to 0. This is the theorem statement, right? Okay, so that means we can find the characteristic equation using this one. Here S1, that is the trace of the matrix. So here we have find the trace of the matrix, that is 3. The S2 is the sum of the minors of the diagonal elements, that is 2. So S1 is equal to 3, S2 is equal to 2, and the third one is determinant of A, which is equal to 0. By using all this result, if we put all this value in this equation, we will get the characteristic equation as I written here. That is, characteristic equation is lambda cube minus s1 lambda square, right? That is equal to -3 lambda square plus 2s, okay, s2 is equal to 2. So this equals to plus 2 lambda, that is s2 lambda, and plus minus determinant of A, which is equal to 0. So now this is equal to 0. This is the characteristic equation for the given matrices. If we take lambda common, then here lambda square minus 3 lambda plus 2, that is equal to 0, implies lambda here lambda minus 1 lambda minus 2